All right, besides just using second derivative for velocity and third derivative for acceleration, we can use higher derivatives for other things on functions, like concavity. We can say that a function is concave up on an interval if it's shaped where it kind of looks like a bowl, where it holds water, or concave down on an interval if it looks like it's a bowl that's upside down or spills the water. We have concave up and concave down. We've seen how we can use the first derivative of a function to figure out if a function is increasing or decreasing, right? Well, the second derivative gives us the rate of the first derivative, so how fast the function is increasing or decreasing. So that's what's going to tell us if it's concave down or concave up. How fast is it increasing or decreasing? So our second derivative is going to tell us concavity of a graph. The first derivative tells us if it's increasing or decreasing. The second derivative is now going to tell us if it's concave up or concave down. Do you see the point in the middle where it changes concavity from concave down to concave up? That point in the middle is called the point of inflection. So anytime a function changes concavity, we have what's called a point of inflection. Okay? If you look at these, we have a function that is concave up. Now, just because it is concave up doesn't mean that it's increasing. A function can be concave up and decreasing. It could be concave up and increasing. So increasing, a first derivative being positive or negative, doesn't necessarily determine what the second derivative is, concave up or concave down. You would have to check for both if you were looking for both ideas. The middle one is also another example of an increasing function, but this is increasing concave up and increasing concave down. So again, we can have different concavities with increasing and decreasing. The last one is a decreasing concave down and then an increasing concave down. So we have lots of different concavities with increasing and decreasing. Again, you've got to look at both if you're deciding what characteristics are happening on a graph. If you're looking for where a function increases or decreases, remember we use the first derivative. If we're looking for where a function concaves up or concaves down, we're looking at the second derivative. Now the test for concavity. It says here, let f be a function with derivatives f prime and f double prime existing on all points in the interval. Then f is concave up on that interval if the second derivative is positive. So it's concave up when the second derivative is positive. It's concave downward if the second derivative is negative. So remember, just like increasing or decreasing, if my first derivative is positive, I know that my original function is increasing. If my first derivative is negative, then I know that my original function is decreasing. Well, now, if I can find the second derivative, and I can figure out where it's positive or negative, if the second derivative is positive, well, then I know it's concave up. If my second derivative is negative, then I know it's concave down. I can look at the first derivative value and the second derivative value, and now decide increasing, decreasing, and concave up and concave down. Let's do an example. Example number 4 asks us to find all intervals where this function is concave up or concave down, and then find any inflection points. Remember, that's if there's a change in concavity. Before we can figure out concave up or concave down, we've got to find the second derivative. That's what's going to tell us or help us find our concavity. Obviously, before we find the second derivative, we have to find the first derivative. So pause the video, give me your first derivative and second derivative. The first derivative should be 4x cubed minus 24x squared plus 36x. My second derivative is 12x squared minus 48x plus 36. Again, 12x squared minus 48x plus 36. This is my second derivative. If I'm looking for concavity, I know that I want to look at my second derivative and where it's positive or negative. Now, remember, we should never, ever, ever be blindly testing. I shouldn't ever just be plugging in random numbers to see if it's positive or negative. Before I do that, let's figure out where that second derivative equals 0. Remember, we did that when we did our first derivative. We called them critical numbers. Well, when we do it with our second derivative, they are possible points of inflection. They're not points of inflection yet, unless there's a change in concavity. But in order to find those possible points of inflection, we've got to figure out where that second derivative equals 0, or maybe where it doesn't exist. So when I take my second derivative and I set it equal to 0, I can factor out a greatest common factor on this one of 12, and then I can basic factor again, I can set each factor equal to 0, and I ended up getting x equals 3 and x equals 1 as my possible points of inflection. Now, I don't know if there's a change in concavity until I figure out what the value of my second derivative is, positive or negative. So we're going to do a similar idea that we did with our first derivative test. We're going to take our second derivative, we're going to put our possible points of inflection on our sign chart, 1 and 3, and we're going to test values in each interval in our second derivative. We want to figure out in each interval, is our second derivative positive or is it negative? If it's positive, I know my graph is concave up in that interval. If it's negative, I know my graph is concave down in that interval. So I want to take a number less than 1 and plug it in. I'm going to choose 0. I'm going to take a number between 1 and 3. I'm going to choose 2 and plug it into my second derivative. And I'm going to take a number greater than 3. I'm going to choose 4 and plug it into my second derivative. All right, let me show you a trick. We've been doing lots of stuff where we're plugging values into functions, into our original functions, into first derivatives, and into second derivatives. And many of us, so far, have been taking our calculators and entering in the whole entire equation, right? At this point, you're probably taking 2 and you're plugging it into your second derivative. You're doing 12 times 2 squared minus 48 times 2 plus 36. And then you're doing it again for 4. 12 times 4 squared, blah, 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 right? And that takes a little bit of time. But let me show you a trick that you can use your fancy calculator for that will help us quickly evaluate 0, 2, and 4 without having to enter it in every single time. And then eventually, when we want to find points of inflection, because points of inflection are points, x comma y's, we're going to want to plug our x value in to find our y value that it corresponds to. And if it's a point in our original function, we're going to want to plug it into our original function. And again, without having to plug it into this whole entire equation, how can we do that more quickly using our calculator? Well, I'm going to pause on this idea for a second of this example, and I'm going to show you how we can evaluate 0, 2, and 4 in our second derivative pretty darn quickly using our calculator. So get out your calculator. I'm going to use a TI-84 Plus. You've noticed that I've entered in my original function. I think this is my original function. Let me double check. Okay, is this my, sorry about that. This is my original function, right? Okay, just making sure that I entered it in right because I lost my screen. I have my original function entered into my y1. What we're going to do is we're going to enter in our derivative in our y2 and then our second derivative in our y3. But we're not actually going to enter the equation. Let me show you. What I'm going to do is when underneath my y2, do you see how it's blinking? I'm going to go to Math. I'm going to go down to N derive. It's number 8 on my calculator. And I'm going to push enter. What this is going to do for me, it's going to find the derivative of whatever equation I want it to. And I want it to find the derivative of my first equation, my y1, right? My original. So then what I'm going to do is tell it to find the derivative of my y1, whatever equation I put in there. So I'm going to go vars. I'm going to go over to y vars. I'm going to go to function and push enter. And I'm going to choose y1. I'm telling it to find the derivative of this equation, of my y1 equation. I'm going to enter a comma. I'm going to tell it to find the derivative with respect to x. I'm going to do another comma, and I'm going to say find the derivative at all x values, and I'm going to end my parentheses. So I'm finding the derivative of my y1 function for all, with respect to x, for all x values. This y2 then is going to be my derivative of whatever function I put in my y1. In this problem though, we're doing second derivative, aren't we? So right here in my y3, I want to do the derivative of my y2 now, so I can put the second derivative here. I'm going to do that same process. Remember math. I'm going to go over, or down, excuse me, to N derive. I'm going to go to vars. I'm going to go to y vars. And instead of y1, I now want to select y2 because I want to find the derivative of y2. That would be my second derivative. I'm going to find the derivative with respect to x for all x values. Now, your calculator might look a little bit different than mine. My calculator has a little bit of an older software in it. Your calculator might look like this when you go to do your derivative, your math and your n derive. It might look like this. You're going to put an x here, you're going to put your y1 here, and then you're going to put another x here. Down in y3, it's going to look the same, except for this is going to be y2. I've actually have steps right here, so you can pause the video and look at those. Or I've actually uploaded this worksheet into Canvas, so you should be able to follow along the directions so that your derivative looks just like this, and then your second derivative, the only difference is you'll have y2 in there by clicking the vars and the y vars and the y2, just like I did. Okay? So whatever calculator you have, hopefully you have both of your derivatives in there now. So remember, what we were trying to do in our example is we were trying to evaluate 0, 2, and 4 in our second derivative, right? And our second derivative on our calculator is this y3. So what I want to do is I want to go over the top of the equal to sign in my y1 and in my y2 and push enter so that I can turn it off. I went over the top of the equal to sign and I pushed enter. Do you notice that they're not highlighted now? The only equation that's highlighted in my calculator is my y3. That's my second derivative because that's the one that I want to use right now. So my y3 is highlighted, that's my second derivative. And I want to find the value of my second derivative when x is 0, when x is 2, when x is 4, without having to put in the equation. So I'm going to go to second, I'm going to go to trace, and I'm going to go to value, that's number 1. And I'm finding the value now of my second derivative. Give it a second. We're going to enter in at x equals 0, at x equals 2, and then again at x equals 4. It might take a while to calculate the derivative and then the second derivative. That's what mine is doing. It's thinking here. Hopefully it's not frozen. You see it's thinking. Once it pops up, we're going to enter in 0, 2, and 4 and be able to quickly tell if our second derivative is positive or negative. Ah, there it goes, finally. Do you see how it says an x equals? We want to evaluate our second derivative when x equals 0. We got 36, right? We also want to enter and evaluate the second derivative when x was 2. So I'm going to enter 2. I got a negative 12. I also want to evaluate it when x is 4. I got positive 36. Do you see how quick that was? Evaluating all three x values very quickly in my second derivative. I entered in 0, I entered in 2, and I entered in 4 into my second derivative. You can do the same thing when we're looking to see if my function is increasing or decreasing. Remember when we test our intervals in our first derivative to see if our first derivative is positive or negative. You can do the same exact thing. The only difference is you're going to want to highlight your y2 instead of your y3. Pretty cool, huh? All right, let's go back to that example. Let's finish it off. So remember when we entered in 0 into our calculator, it gave us a positive 36. When we entered in 2, what was it? Negative 12, I think it was. And when we entered in 4, I think it gave us another positive. I thought it was positive 36 also. So my second derivative is positive, then negative, then positive. Remember, if my second derivative is positive, my original function is concave up. So I can say my original function is concave up from negative infinity to 1, and then again from 3 to infinity, because my second derivative is positive. My original function is concave down from 1 to 3, because my second derivative is negative. All right. Now, the last part of the question asks us to figure out any points of inflection. I abbreviate it into POI, points of inflection. Remember, points of inflection only happen when my second derivative changes concavity, either from concave up to concave down or concave down to concave up. And you might notice that there was a change in concavity here. It went from concave up to concave down, and then there was another change in concavity here at x equals 3 from concave down to concave up. So I know there's actually 2 points of inflection on this graph, at x equals 1 and at x equals 3. But remember, points of inflection are points. They should be written as points, x comma y's. and they are points in my original graph where it changes concavity. So I need to figure out what y value goes with my x value of 1 and 3 in my original function. So what that means is we want to take 1 and plug it into our original function so we can figure out where on our original graph it changes concavity. We also want to plug in 3 to our original function so we could figure out where it changes concavity there. So instead of doing it the long way, let's use our trick with our calculator and plug it into our original function, 1 and 3. Here we go. So I have my calculator. I want to evaluate in my original function, so I want to make sure I turn off my derivative and my second derivative and turn on my original function. So I went over the top of the equal to sign and I pushed enter. Now that my original function is highlighted, I'm going to go second, trace, and I'm going to find the value in my original equation. It's taken a while to think. Okay, I want to find the value at x equals 1, 11, and I want to find the value at x equals 3. You notice I don't have to do anything. I just have to push 3 and it'll give me a new value of 27. So I have 2 points of inflection. I have points of inflection at 1, 11 and at 3, 27, all without having to type it over and over and over again in my calculator. As long as I can program my original function, I have my derivative and my second derivative already programmed, I can quickly, easily evaluate in any of those 3 equations. And now, anytime you go to do a new question, all you have to do is clear out, oops, I don't want to do that. All you have to do is clear out your y1. Do not clear out your y2. Save it, keep it in there just like that, and you never have to re-enter it again. All you have to do is enter your new function in your y1, and your calculator will find its derivative and its second derivative. If you keep these in here, you won't have to reprogram it at all. All you'll have to do is enter your new original function. I hope that you enjoy that. I hope that works for you. I hope that makes it easier and quicker for you to evaluate these functions without having to do it by hand in your calculator over and over. Let me know if you have any questions. And for those of you that have the newer software, make sure that you check out the document and the steps that I have for if your calculator looks like this, so that you can still do it even if you have the updated software.